we continue with our discussions about designing a reinforced concrete member subjected to the combined effect of shear and torsion. We mentioned that we cannot design the shear and torsion separately, as we might have overestimated its resistance. In the reality, a member's resistance under the combined shear and torsions, it will be lesser as compared to when it is subjected separately under torsions and shear. Therefore, there is a need for the interactive formulas. And if you have observed, there are two interactive formulas. One is meant for the sections with shear reinforcement. Another one is meant for the sections without shear reinforcement. Now, how do you know which to use? We have very simple principles here. If the sections has a relatively small cross-section as compared to the shear applied onto the member, it is very likely there will be shear reinforcement. This kind of member include beams, columns, and if the members has a relatively large cross-sectional area as compared to the shear load, normally shear reinforcement is not required. The member will depend on the concrete and the section itself to resist the shear load. Under these circumstances, you will use this interactive formula. In these videos, we're going to continue discuss about the applications of this interactive formula, as well as the fundamental principles governing it. You know that whatever derivations that we have, for example, for the longitudinal reinforcement, for the torsional link, and even the compressive strength of the strut on the shear part, the compressive strength of the strut, the shear reinforcement, and so on and so forth. They are discrete to specific components of the member. We have been mentioning that we cannot design for the shear and torsions separately if the member is subjected to a combined torsion and shear together. This is prevent us to overestimate the resistance given by the member. Now the question here is, how do we design them in combined when all our previous derivations are all separated? This comes to an important concept that we need to explain in this video. In order to overcome this problem, we must first ensure that the interactive formulas for the section is fulfilled. By doing so, we can guarantee that whatever the design outcome will always fall at this region. At the same time, we eliminate the possibility that our design will go out of this boundary. Once you confirm the interactive formulas are fulfilled, then you have no issue to design the shear and the torsional link separately. Because no matter what is the outcome of your design, it will always fall within the safe region here. That means it is the matter of chicken and egg. You cannot design the torsion and shear separately without checking for the interactive formula, as there is a risk that it goes beyond the acceptable boundary. In order to overcome this, your first criteria it would be making sure that the sections fulfill the requirements of the interactive formula. Only then you will design for the shear and you design for the torsional link. And then if you observe the formula, both the resistance to torsions and resistance to shear have the strut angle. We assume that the strut angle under shear and torsions are the same, which shall be between 22 degree to 45 degree. Therefore, while designing for the shear resistance, you may use this formula to determine the strut angle, and based on the strut angle that you have obtained, you're going to adopt it in the calculations for the torsional resistance. Next, we look into the differences between the interactive formulas that we use for the design. First, this formula is used for the sections with shear reinforcement. This includes beams and columns. This kind of member have characteristics where the torsional and shear stress are relatively large as compared to its cross-section. Because of the insufficient cross-sections to take the shear load, shear reinforcement in the form of link will be required. And because of the presence of the shear reinforcement, an imaginary thrust model is formed within the member. You will have reinforcement taking the tensile strength and concrete taking the compressive strength. The maximum capacity under torsions and shear are derived on basis of the compression limits of the concrete. In contrast, these formulas are meant for the sections without shear reinforcement. This includes the slab, stairs, and load-bearing walls. This kind of member have relatively small torsional and shear stress as compared to its cross-section. As a result, no shear reinforcement shall be required. Not only the applications of these interactive formulas, your subsequent steps, whether the requirements are fulfilled or not fulfilled, vary slightly, and this shall be the focus of our discussion. First, for the sections with shear reinforcement, if the requirement not exceeding 1.0 is fulfilled, it gives us an idea the member will not fail in brittle manner, as you do not expect the concrete to crush under the compression. Therefore, you may proceed with the design of the shear and torsional link. You're going to design them separately, and later, the total amount of reinforcement required shall be the summations of the shear and the torsional link. And the strut angle you will assume the same for both torsional and shear design. Now, if you compare with those without shear reinforcement, the interactive formulas here serve as the acceptance criteria. It helps you to check whether the resistance of the sections is sufficient under the combined effect of shear and torsion. Since there is no shear reinforcement, there is no need for you to design for the shear reinforcement. In the absence of the reinforcement, you also do not need the torsional link. Now, the only thing that you can do, it is merely use this formula to check whether the sections has sufficient resistance or not. Now, what if the requirements are not fulfilled? You may look into the components within the formula. If this formula is not fulfilled, your option here, it would be either to increase the torsional capacity or shear capacity. I guess the simplest way it will be for you to increase the sectional area. By increasing the cross-section area, you're going to increase both the torsional capacity and also shear capacity. Only that they increase them in a different manner. You may look at the equations for the torsional capacity and the shear capacity. Increasing the dimensions of the section, that means you're increasing the width and also the effective depth of the section. This is going to increase the shear resistance capacity. Increasing the cross-section area, at the same time, you're going to increase the effective area of the hollow section. This also going to increase the torsional resistance capacity. You have other options for you to increase the resistance in order to make sure this pass. By looking into the formulas, you will see the importance of the concrete strength. By increasing the concrete grade, you will also increase the torsional resistance and the shear resistance. You might want to ask, if you increase the amount of reinforcement provided in the section, would it be helpful for this formula? The answer is no. Providing additional reinforcement bar does not increase the maximum torsional moment and also maximum shear strength. Why is it so? Because the maximum torsional moment and maximum shear strength are derived on the basis of compressive strength of the concrete. It is referring to the compressive strut, which is this within the imaginary truss model. You may refer to the formulas for the maximum torsions and the shear. It is not relevant to the amount of reinforcement bar provided. Even though you add reinforcement, TRD max and also VRD max will still be the same. Therefore, if you find these interaction formulas fail, adding the reinforcement bar offers no contribution in passing the interaction formula. How about for the section without shear reinforcement? If you find the interactions model here fail, one way to overcome it will be to increase the sectional area. This is reflected with the calculations of the shear capacity. Increasing the sectional areas leads to a greater effective depth. This shall subsequently increase the shear resistance of the member. Same applies to the torsional resistance. Increasing the sectional size, particularly increasing in terms of the height, shall lead to you increase of the effective area and subsequently increase the torsional resistance capacity. Another way is for you to increase the longitudinal bar in order for you to strengthen the section. However, you will know that the contribution here it will be quite limited. Why is it so? You may refer back to the formula here. Among the formulas constituting the maximum capacity of the shear and also torsion, only one formula considers the effects of the reinforcement, as reflected by the row 1 here. The area here represents the area of the longitudinal reinforcement, and this influence is kept at 0.02. That means the amount of reinforcement bar, if exceeding 2% of the cross-sectional area, further increment of the reinforcement will offer no additional contributions. Therefore, if you choose to increase the amount of reinforcement bar within the section, it will increase your VRDC, but not VRDC mean. It is only when this VRDC is greater than VRDC mean, then the increase of the amount of reinforcement bar will lead to increase of the VRDC, which is the shear capacity. However, on the torsional side, the longitudinal reinforcement bar contribute no effects. Another options it will be you increase the concrete strength. Increasing the concrete strength will help you to increase the resistance under shear. It may also increase slightly the torsional resistance. Normally, the tensile resistance of the concrete is about 1/10 of its compressive strength. That means the increment in terms of the concrete strength actually contribute very marginal increase in terms of the torsional resistance. However, this does not deny the fact that you can actually use higher concrete strength to increase the capacity of the section. All in all, I would still say that increasing the sectional area it will be more effective in increasing the shear resistance and torsional resistance. This applies to both cases.